Good morning, good afternoon, and good evening. Tom Concolino, and I'm here with our presenters, Aya Takase and Angela Criswell.
Hi, everyone.
Thank you all for attending Rigaku's webinar series on X-ray computed tomography for materials and life science. This is the third and final session of our deep dive into digital rock analysis, and today we're focusing on simulations. So this session will be taking place in the lab with Aya and Angela reviewing in real time how to calculate capillary pressure, determine permeabilities, as well as performing some simulations. They'll also offer their thoughts on dealing with the unique challenges of performing CT experiments on material science samples. Now, please note if you missed any of the previous webinars, you can view them on the Rigaku website. We also want to welcome Dr. Arne Jacob from Math to Market as a guest panelist. He'll be able to add additional thoughts and answer questions throughout the session as well. But before we start, a few housekeeping items. Now, as far as today goes, like our previous workshops, this is going to be an interactive session. So we'll still be taking your questions during the webcast and answering them during the session. So please don't wait until the end to ask. And as usual, please submit those questions via the Q&A button at the bottom of your screen. Now, I won't be monitoring the raised hand function, and I'll also be posting relevant links in the chat window. Now, we'll be trying to answer as many questions as we can during the workshop, and we'll respond to any unanswered questions after the session is complete. If for whatever reason you have difficulty viewing the webinar live, please note that it is being recorded, and you'll be able to view the recording beginning tomorrow. And with that said, I'll turn it over to Angela and Aya.
Thanks, Tom and Angela, and thank you, Arne, for joining us. It's great to have you. And thanks to everyone for joining us for the workshop. So we are presenting live from our office in the Woodlands, Texas. And this is the last part of the episode series for digital rock analysis. So in this series, we reviewed in the first episode how to do the data collection for digital rock analysis. And we took a look at segmentation and some basic property analysis in the last episode. Today, we're going to focus on digital rock simulations. So in this workshop, you will learn how to calculate capillary pressure and how to obtain relative permeabilities. You will also see how to simulate the drainage and inhibition processes. And all the CT scans you're going to see today were collected on the CT Lab HX, and the data analysis were done using Geodict. And you will see a demonstration of this software in the later half of the workshop. Okay. So this is the last episode of the series. And I just want to take a step back and think about this question. So what are digital rock simulations for? Why are we doing this to begin with? So if you have a reservoir rock, something like sandstone, for example, and if you do a CT scan, you will see the sand grains and the pore space. And if you look at it closely, you can see the pore space running around in the sandstone. And in that space, if it's a reservoir rock, you will have water, oil, and sometimes gas. And the point of doing all these analyses is to figure out the best way to extract that oil out of the sandstone or any other reservoir rocks. So that's the end goal we have in our mind. And that's why we are going through all those analyses. And in the last episode, we learned how to segment the CT image to separate the space into pore space and the solid. And you can, based on that structure and the segmentation results, you can calculate the absolute permeability. So today, we're going to look into how to calculate the capillary pressure curves and also relative permeability. Just terminology-wise, the part we covered in the last episode, that involves only single phase flow, and they are sometimes called as routine core analysis. The part we're going to cover today involves two phases, and they're called the special core analysis, and that's what we're going to talk about today. Now, what does this process involve? So this process involves both drainage and inhibition processes. Now, before I explain what they are, Angela, let's ask the audience a question.
All right, that's our first poll question. And we would like for you to pick one of these options. What is a drainage process? Is it when water replaces oil in the pore spaces, or a wetting fluid becomes non-wetting, or a non-wetting fluid replaces a wetting fluid? So lots of votes are coming in. That's good to see.
It's a bit of a tongue twister.
It
Those
is. It is for sure. All right, so we have kind of a 50-50 split on a couple of these answers.
Yeah.
We'll give everybody a few more seconds and just see if we can pick up a few more votes. And now I'm going to go ahead and end the poll, and I'm going to share the results with you, the audience. So the majority thinks it's when water replaces oil in the pore spaces, but I is going to let us know for sure. I'll stop sharing these results.
Okay, so I'm gonna say you guys got the replacing part right. So drainage process is the process when non-wetting fluid, oil, for example, replaces wetting fluid, water, for example. So let's say that in this rock, you have solid and all the pore space is filled with water. Then oil comes in to replace water in this case. And when this happens, by the way, there is always a little bit of water left behind, and that's called the residual water. Now, if you let this process go on, you will have more oil replacing water. And at the end of the day, most of the space gets replaced by oil. But however, you still have this residual water in it. But anyway, drainage process is the process where non-wetting fluid replaces wetting fluid. So we can think about the opposite of this. Let's say that the pore space is filled with oil or non-wetting phase. And if this gets replaced by wetting fluid, for example, water, that's the inhibition process. So water comes in, this time from the bottom. I'm just keeping the directions the same. And when water replaces oil, again, the same thing happens. A little bit of oil gets left behind, and that's the residual oil. And as the process goes on, you will have most of the space replaced by water with some oil left behind. But this entire process is called the inhibition process. So they're similar, but definition-wise a little bit different. Okay, now I'm using those terms wetting and non-wetting fluid, but just in case you might be wondering, what's the difference between the two? Let's ask the audience the next question.
All right, that's our second poll question. I'm launching this now. So what do you think differentiates wetting from non-wetting fluids? Is it viscosity? Is it permeability? Is it contact angle? Or is it instead density? So we'll give everybody a chance to vote. So we've got almost half of the people participated so far. Looks like there's a clear winner this time, for sure. All right, so I'll give a couple more seconds, and now I'm going to go ahead and end this poll. I'm going to share the results with you, and the audience overwhelmingly thinks the answer is contact angle. So what do you say?
That is correct. So let's define this. When you have a wetting fluid on the hard surface, it would look like this. And this is the contact angle. And when the contact angle is less than 90 degrees, we said that's wetting fluid. It wants to wet the surface. On the other hand, when you have no wetting fluid, you have the contact angle greater than 90 degrees. So that's what differentiates those two types of fluids. Now, depending on which one is replacing which one, we call it either drainage or inhibition process. But is inhibition simply an inverse process of drainage? Well, the answer is not exactly. So in the drainage process, you have the non-wetting phase and the wetting phase. This non-wetting phase, to get through that narrow throat, to get to the next pore, for example, the non-wetting fluid needs to be kind of pushed into that narrow space to invade the water space. In other words, the capillary pressure needs to be greater than the pore's threshold pressure. Otherwise, the oil cannot get into the pore to replace water. Now, let's think about the same scenario for inhibition process. So in this case, water is trying to replace oil. In this case, water almost kind of gets sucked into that narrow space. It doesn't need to be pushed in. So the wetting fluid enters the narrowest pore, or throat, I should say, or the tiny pores first. You don't need to really push it in. And this difference is all related to the capillary pressure. But what is the capillary pressure? I'm not going to answer that question because I want to ask you first.
All right. As you might have guessed, that's our next poll question. What exactly is capillary pressure? Is it the pressure between two immiscible fluids in a thin tube? Or instead, is it the pressure to apply to a capillary? Or is it the maximum pressure the wall of a capillary can bear? So we'll give everybody some time to answer. We've got about 30% of the participants voting so far.
About half
Right.
now.
About half now.
Yeah.
So a few more answers are trickling in here and there. So, but it looks to have settled down. So I'm going to end this poll and I'm going to share the results with you. So the audience thinks it's the pressure between two immiscible fluids in a thin tube.
Okay, that is correct. You're doing well today. So capillary pressure in this context, that means the pressure between two immiscible fluids, the fluids that cannot mix together in a thin tube. So I don't know if you remember you've done this experiment in maybe high school or junior high, but if you take a glass of water and put a straw or thin, tube into this, the water comes up inside of this tube. That's because water wants to wet the surface, the internal surface of the capillary or the tube. And the water is being pulled up in a way against the gravity. So it's going to stop at the point when the forces that's working on that little piece of water, pulled up in the capillary is balanced. So that's what happens when you have wetting fluid, which wants to wet the surface of the capillary. On the other hand, if you have, let's say, a glass of oil, non-wetting fluid, and if you do the same experiment, then air gets pushed in and the oil surface goes down because oil does not want to wet the surface of the inside of the capillary. And again, there is two forces being balanced at the interface. So this is just straw, a capillary, and a glass of water experiment. But with this in mind, let's go back to those figures. So either you're looking at the drainage process or imbibition process, always there is a balance of two forces or pressures at the interface of those two fluids. And that's why the capillary pressure is so important if you want to simulate those two processes. Now, in the old days, maybe still so today, if you want to know the capillary pressure, you can measure the capillary pressure. And that has been a common way of doing it. And there are several different ways to measure the capillary pressure. And you're looking at just a couple of examples. And if you want to know more about those techniques, I would recommend you taking a look at Perm Inc. website. They have a really good handbook about how to run those experiments and all other rock analysis experiments. Now, among those four, the mercury injection method is one of the commonly used technique. And the way this works is, I'm going to explain how this works with a cartoon. You would have mercury, which is non-wetting phase in this case, and you try to push it into the pore space, which is evacuated, and it just has air at this point. And you can measure how much pressure goes in and see what happens at that throat of a pore. And then measure the added pressure and the mercury volume change, meaning how much of a mercury was absorbed into the rock, you can measure the capillary pressure. So that's one way to figure it out. Or you can simulate the entire process. So I'm going to show you an example of a simulated version of this experiment. So this is the segmented structure of Idaho gray. This is the one we've been looking at for the last 2 months. And using this structure, you can simulate what happens when you try to put mercury into this piece of rock. So you see the mercury going into the pore space and the capillary pressure calculated for different points. So this is a simulated version of more or less the same experiment. And if you were to replace experiment by this simulation, you would wonder, how accurate is this simulation? How well do they match? So luckily, there are people who did this comparison, and let me show you the results. So in this graph, you have wetting phase saturation as your x-axis, and you have the capillary pressure as your y-axis. This black line is the result of an experiment published by Berg and his group. And this was in 2016. And the red line is showing the simulation done by Geodict with the latest version with the mirror model. I want to mention that if you go to the original 2016 paper by Berg, you will see the simulation showing a little bit greater discrepancy than what you're seeing on this slide. But since then, Geodict added a lot of improvements to their simulation. And then now with the latest version, you can do a simulation that matches this well to the experiment. So I hope this is comforting for you if you're thinking about replacing the experiment by the simulation. So they do match very well. Okay. Now we have two phases in the system. We're talking about having air and oil both in the pore space. So can we simulate both the drainage and inhibition processes we are talking about here? And the answer is yes, we can. And to simulate this, the pore morphology method is commonly used. And at the beginning of the development of this method, people used quasi-static pore morphology method. And with this method, we're making some assumptions, I should have mentioned. One is the gravity and the viscosity forces are supposed to be negligible compared to the capillary force. And also we assume that the material fluids are pretty homogeneous and we can define the contact angle very well. The other assumption is that we are thinking about only two phases, no more than two. So with those assumptions, we can apply a Young-Laplace equation. And using this equation, you can calculate the minimum radius of accessible pores by using the capillary pressure, either you measured it or simulated it, and the surface tension and the contact angle. Now, this is a very convenient way to do this type of a simulation. However, it has a drawback. Now, so Angela, let's ask the audience if they can guess what the drawback is, or you might know what it is.
Right. So what do you think it is in this case, that drawback? Is it because it's static and it cannot be used to simulate a drainage process? Or is it can be used only for drainage processes? Or is it in fact that the saturation jumps when a fluid passes through the narrowest throat? So we'll give everybody a chance to some time to vote. We've got about half of the people voting at this time. If you're there, definitely pick one of these options. We do have looks like a clear winner here.
Yeah,
for sure. So I'm just going to give everybody a couple of more seconds. And now I'm going to go ahead and I'm going to end this poll and share the results. And the audience thinks the drawback is that the saturation jumps when a fluid passes the narrowest throat.
that is correct. So I guess you already knew the answer, or the hint was in the name. It's quasi-static, so there is a jump. So let's see. So I'm going to show you the video on Arnold was kind enough to let us use some of the videos they created, and you will see the black fluid going into replacing the blue fluid phase, but it's going to jump at one point. Okay. So at the beginning, it looks kind of okay, right? It doesn't jump too much, but as soon as it passes one spot, it jumps and everything else gets filled all of a sudden. So that's the drawback. To overcome this problem, you can use dynamic pore morphology method. So with this method, we're assuming non-monotonic capillary pressure, and we are dealing with the mixed wettability and the forced inhibition. And one of the important things on it is this third one. This method is considering critical events like the fluid bursting or touching each other when there are two areas of fluid coming together or overlapping. And when all those things are considered, you can do more dynamic simulation. So I'm going to show you the result of it using the same example. So in this case, it doesn't jump. You can see the entire process with multiple time steps. So this is an example where when you use the dynamic pore morphology method, you can do, I don't know if I can say more accurate simulation, but definitely you don't need to deal with this jumps of the saturation. Okay. Now, again, we're trying to simulate everything. So the question to ask at this point is, how well do simulations match the experiments? So I'm going to show you an example. This was done on, this was published in Young's paper in 2016. So to compare the simulation to experiments, they prepared, I heard two different versions of pronunciation for this, either heel shoal or hell shoal. Like heel.
We will believe you.
How would you say it, Arn?
I don't know. I think both sounds fine for me.
Okay.
Really...
I'm gonna go with the heel shoal. So a heel shoal cell, which has two plexiglass, plates, and you can put different, places, the columns randomly in between. Then, just as an example, you could put one liquid, dodecane on one side and push water into it, for example. Then you can visualize this either drainage or inhibition process. So this is the experiment. And I'm going to show you the comparison between the experiment and the simulation. So you see the experiment at the top and the simulation at the bottom, and those three versions have different contact angles. Considering how randomly those columns are placed, and also we're looking at very wide range of contact angles, I think the simulation is matching the experiment very well. And this, can tell us that it's probably, safe to replace maybe not all of them, but at least some of the time-consuming and expensive experiments by simulation. So with that in mind, with the peace of mind, let's move on to the capillary pressure curve calculation. So what is capillary pressure curve? So this is the relationship between the capillary pressure and the fluid saturation, because we're talking about two types of fluid. So they have saturation percentages for each. To show the curve, usually you would put the wetting phase saturation as your x-axis, and you put the capillary pressure as your y-axis. At the beginning, if you replace everything in the pore space, let's say with oil, we call it primary drainage process. So you're reducing the wetting phase saturation. Then you can go through the inhibition process, which means that the oil is now replaced by water and the wetting phase saturation goes up. You can also do the drainage again, the secondary drainage, to push the water out of the system. One of the things I want to point out here is that this process is not completely reciprocal, meaning that you see hysteresis, and that's because the inhibition and drainage processes are not exactly the same thing. Also, the primary drainage needs to be forced. You need to add a pressure to make this happen. For the inhibition process, at the beginning, this happens spontaneously until the pressure hits 0. And after that point, you have to force the process to get all of the oil out of the system. Okay, so let's take a look at the primary drainage. This is something, again, using the theories we just briefly looked at, you can simulate. So this is a simulated result. We have the wetting phase saturation as your x-axis, and you got the pressure as y-axis. At the beginning, it's going to look a little bit weird, but the beginning is on the right side of the graph when the wetting saturation is 100%. You have a bunch of water in the pore space, and I'm showing water in blue. The purple bits you're seeing there are the water in closed pores. Those are not accessible. Okay, then you go through this process and take one step, and you see oil, in this case, dark green, coming into the system to replace water at the top. And if you keep going, you will see more oil coming into the pore space. And at the end of this process, most of the water was now replaced by oil. However, you still have a little bit of water left, meaning that this data point is not going to 0. And it's probably easier to see this in the cross section, but you can see in this cross section, most of the pore space is filled with oil, but there is this purple parts that are representing the residual water. And that's the water you can't really get out of this pore space. Now, we have a water and the oil both in the pore space. That means we got the two-phase flow. And this means that, yes, we can calculate the relative permeability now. A little bit of a recap from the last episode. So absolute permeability is defined when you have only one fluid in a space. The relative permeability is a ratio between the permeability of one fluid at certain saturation point divided by its absolute permeability. So it's a relative number, and it depends on the saturation percentage. This is also something you can easily simulate. And this is an example of water and oil on effective permeability simulation results. So the x-axis is the wetting phase saturation, and red line is representing on the wetting phase in this case. So when the wetting phase saturation goes up, its effective permeability goes up too. On the other hand, for the non-wetting phase, oil in this example, when the wetting phase saturation goes up, the non-wetting phase effective permeability goes down. And those are the effective permeabilities calculated for certain saturation point. And with this and the absolute permeability, you can calculate the relative permeabilities. You can also pick one saturation point and visualize the velocity map, meaning that you can see how fast the fluid is traveling in this space, depending on the location in the rock. Okay. So going back to this capillary pressure curve plot, let's take a look at this part. This is actually the important part. By calculating this entire curve and those two, red and the blue lines, you will know, first of all, what the irreducible water or the residual water saturation is. And more importantly, you will know what the residual oil saturation is. And that's the amount of oil that's going to be left behind in the pore space after you go through the inhibition process. So again, using that Idaho gray structure, if you run all the simulations, you will have a result that looks like this. So we're using this segmented structure, and we go through the inhibition process. At the beginning, this part happens spontaneously. Then as soon as it hits pressure 0, then you start forcing the process. But no matter what you do, at the end of the day, there is 0.149 or 14.9% of oil left behind in the case of this Idaho Gray simulation. Okay, so that was, I think, a very quick overview, although we took 3 episodes, a quick overview of digital rock simulations. And now you know how capillary pressure curves are calculated, and also you know what relative permeabilities are and how they are calculated. So I'm going to move on to the kind of hands-on simulation part of the workshop. But before I do that, let's see if we got any questions.
We did. We got a few questions here. So the first one is in the Young-Laplace equation, you mentioned that viscosity was negligible. Is there a viscosity where it eventually does become or need to be considered?
Not negligible?
Not negligible, yes, where it needs to be considered.
So I think that is a question for me.
I think so too.
Yeah. So as an explanation, our approach, the Pore morphology method, only uses the Young-Laplace equation because it is a pure geometrical approach. So there are no viscous forces included here. So we consider that we do not have the viscous forces dominant in that regime. That is why we do not have to think about if the Young-Laplace equation has an effect at some point, because our approach doesn't use it at that point. Because we would have to combine different approaches by, let's say, computing the Navier-Stokes equation and combine it with the Pore morphology approach. But yeah, since they are completely different, you cannot match them together here.
Okay.
Hope this answers your question.
Yeah, so what you're suggesting is that you're not considering them as part of your simulation. There would be it'd be a completely different simulation if you were to include viscosity as another equation as part of your simulation, right?
Yes, right.
Okay, okay. All right, excellent. The next one is, and I hope I'm getting this phrased correctly. They're asking how a two-phase simulation using the extracted Pore network can be integrated or upscaled with or /for full field scale reservoir simulation. So I think this has to do with the scale that we are modeling to how well does that.
Yeah, we're looking at this tiny space.
Yeah.
Yeah. So I think I already answered the question, but I think I could give you additional information here. So of course, what we know is we have the capillary pressure curve, and we can also determine the full hysteresis cycle in geodesic. In the figure here on the left-hand side, you can see the drainage and the inhibition process. You can, of course, also simulate the secondary drainage process and do the complete cycle here. But the important information you can also upscale is, of course, the residual oil and water saturation, because that gives you the information how much oil or water would be left after the drainage or inhibition process here. So that is, of course, a very, very important information you need for your reservoir simulation here.
And I would add that one of the aspects you might want to think about when you are scaling the results is if the rock you're analyzing here is a good representation of the larger scale rock or field you're dealing with. And that's the topic we covered in the first episode. And there is a way to figure out how big of a space you should be analyzing to scale the results to the larger volume.
That's right. I wanted to thank Nilesh. She gave us a third possible pronunciation for Hella, and she's suggesting, or he is suggesting, Hele.
Haley, I think I
Haley.
heard that one too.
Yes, so that's a
Yeah.
third possible pronunciation. So we want to thank Nilesh for that. And I think we'll
We
hold
gotta
on to a
look
few more
into this.
questions, and we can move on to the live portion of the workshop.
Okay, okay. So let me do a new share. Before I do that, let me prepare the screen. Okay, do you see the software interface now?
We do.
We do.
Okay, okay, good. And the first calculation I'm gonna run probably will take about a minute or two, so we can take more questions then. So this is the geodict interface, and I already have that lovely Idaho gray we've been looking at for such a long time already prepared. And this has been already segmented. So we have just the structure for the pore space and the solid space. And using this, let's do the mercury intrusion capillary pressure simulation. So you can go to predict and choose SatUdict. This is where all the tools we're going to use today reside. And when you go to the SatUdict and the pull down menu, you have multiple choices. You have a lot of freedom with your settings and parameters if you choose one of those analysis techniques. But for the first one, I'm going to go to predefined. This is where kind of prepackaged calculations are available. And the people and experts like Arne at Geodict, they set the commonly used or recommended parameters so that you don't need to worry about, 10, 20, 30 parameters to set. And under the predefined menu, you see some of those choices. And one of them is the mercury intrusion capillary pressure. And I'm going to go to edit option menu. And you can see that all you pretty much have to do is to name the file. You can change the name as you like, and you don't need to worry about all the detailed parameters. Now, I'm going to click OK and run the simulation. So this one shouldn't take too long. Okay. Do you have any other questions we can maybe address?
We do. So we've got one other question here is the amount of residual water or residual oil for that matter consistent across different rock types? I mean, I think this whole geodict is to figure out how much residual water, residual oil we're doing. So does it vary widely depending on like porosity or any other properties? Can we get any insight into that?
Yeah, so Thomas, you're completely right. That's where you need geodict for. Of course, it varies a lot across the different rock types. Let's say you have an unconventional carbonate or so, you have much bigger residual for oil and water, depending on which process you start. Let's say if you have a water wet rock or an oil wet rock. So normally in the unconventionals with more or with a higher complexity of the geometry, you're getting much more residuals inside of the structure here.
Okay.
So I guess there's a general trend, but to figure out what it is for your particular type of rock, do you want to?
Yes, that is where you need the simulation for.
Okay. The other question, and this is one that I had brought up earlier, and I wanted to get Arne's thoughts on this. Is there or can a wetting fluid become a non-wetting fluid, and vice versa, depending on the properties of the rocks, the surface properties, right? So would water ever become a non-wetting, for example? Arne, have you, or do you have any experience in seeing that different materials essentially?
So after you've executed the drainage process and you start with forced inhibition, we have the algorithm which changes the contact angles on the oil rock surfaces. So at some points you have the oil touching the rock. And on these surfaces of the quartz grains, you then have oil rock. contacts with a higher contact angle for the water then. So the oil, the rock becomes oil wet, which means that the water doesn't wet the rock anymore because it is oil wet then.
Oil wet.
Yeah.
Yeah, that makes sense. If something is coated with oil, the water beads, water
So
doesn't
we have
wet that
a
surface.
dynamic changing of the contact angles on the surfaces of the quartz grains here.
Okay. Okay. All right. So that's it for questions. Actually, I appreciate that, Arne. I was curious about that as we were
Yeah, we're
discussing
talking about
earlier.
it yesterday.
Yeah.
Mhm.
Okay, so the simulation is done. Now we have saturation for non-wetting phase and wetting phase. And we have the capillary pressure calculated here. And you can create your own graph because you have all the numbers here, but you can also look at the plot in the software. So you have the non-wetting phase saturation at the bottom. You can change that to wetting phase if you want to look at the wetting phase. You can also invert the x-axis as necessary. But this is the simulation results. If you want to see how much of a mercury is going into which pore space at certain point during this calculation, you can look at it by data visualization. And you have all the data points here. Let's pick one of them and take a look. And go a little bit higher so that we can see a little bit of mercury. There we go. Okay. So let me hide this guy. Now you see mercury shown in green in this picture going into those pore spaces, and you can hide the solid to see them like this. Okay. I think we have enough time, so let's take a look at another step. So that was at 7,700 Pascal. Let's go to a lot of higher spot here. Okay. Now you can see a lot of pore spaces filled with the mercury. So this is the mercury intrusion capillary pressure simulation. Again, you can run experiments or you can do simulation like this. Okay. So let's go back to this one and load the original structure. Let's move on to capillary pressure curve simulation. So I'm going to close this and go to capillary pressure curve and go to edit. So this is not a pre-packaged one. So you have more parameters or you have more freedom. And I'm going to choose drainage to do the primary drainage simulation. And I want to say that the fluid can leave a residual. That's kind of whole point of the simulation. And let's take a look at this part too. For the constituent materials, we just did the mercury simulations, got mercury, but we want that to be oil. So I'm going to change that to oil. And for this, it says only air. That's because I'm selecting air here, but let me change that to water. Okay. So we have oil as non-wetting fluid and water as wetting fluid. By the way, I should have mentioned that if you have some fluid that's not in the database or the choices, and you can add different materials too. But in this case, we're looking at oil and water, and their contact angles already typed in here, 40 and 140. For the boundary conditions, I'm interested in just into the Z direction. So let me set it this way. Okay. And I'm going to leave the solver parameters as default. Now, once you set all those parameters, you click OK and click run to run it. But this one takes a little longer than I want to make everybody wait for. So let me open save the results. So I'm going to open the drainage results file. Okay. So once you run the simulation, again, you have saturation for non-wetting and wetting phases. Then you got the capillary pressure calculated. And you can look at it in the plot and you can change the axis as you like. So let's see, we go to data visualization and then take a look at some of the simulations. So again, you have all different data points to choose from to visualize. Let me pick something in the middle and load the results. Okay, so let me hide this. So that you can compare the colors from the PowerPoint slides we had before. Let me get the colors the same. There you go. So oil, dark red, in this case, or brown, that it is starting to replace blue water. And the purple is the water that's going to be left behind, the one that's already been left behind. So you can see the distribution of those two phases. Let's take a look at another one. Let's see, towards the end. And as the process goes through, I didn't see much of a difference, but this brown is going to replace more of the water. So that's the drainage process simulation. Now we have a water and oil in the pore space. So let's see if we can calculate the relative permeability next. And to do that, I'm going to change this one to relative permeability. Okay. So in this case, we need to know the capillary pressure. So I'm going to open the capillary pressure we already calculated. And you can choose for how many points you want to calculate the relative effective permeabilities. Right now we have 5 data points, which are shown in blue in this graph. And if you increase the numbers, you will see more points calculated. You can choose the constituent materials. Again, this should be oil and this should be water. Okay. And you can set the boundary conditions on, if you're just interested in the Z direction, you can check Z here. And when you go to the solver tab, you see Lear solver selected. If you're wondering what the heck Lear solver is, you can go back to the second episode, I think. Yeah, the last episode where we explain differences among different solvers. So once you set all those parameters, you can click OK and click Run. But again, just to save time, I'm going to open the Save the Results. Okay. So this one is relative permeability. There you go. Okay. So once this calculation is done, you already have the absolute permeability shown at the top of the results, and you have the effective and relative permeability is calculated in those tables. The top one, this part is the wetting phase, and the bottom is the non-wetting phase. Again, you can see all of them in a plot like this, and you can see their effective permeabilities for both wetting and non-wetting phases change as the saturation percentage changes. For the data visualization, you can pick one of those spots when the data points from the graph and see the velocity map. Okay, so let me minimize this guy. And we got a lot of things we don't need. Let me just turn them off. Okay, now you can see the velocity map. Let me crop the solid so that you can see this better. There you go. And let me change this too. Okay, that should be a little bit easier to see. There you go. So this is a velocity map showing on how fast the fluid is traveling different spaces. And you can kind of see that when you have a wide throat, you see red. it makes sense that the fluid travels faster when you have, wide space. And when you see a narrower throat like this one, it's bluer, meaning that the velocity is lower. And this is something you can completely map and visualize for different saturation points. Okay, so that's the relative permeability. Okay, so the last one I want to show you is the inhibition process simulation. That's kind of the most important part of this entire series, I guess. So let me change this guy to predefined. And we are going to use forced inhibition capillary pressure simulation. Again, this is one of the predefined packages, which are a lot easier to set up, especially if you're new to this. This has been very helpful for me, for example, because I'm new to this too. So you can just click edit and take a look at the parameters that are left for you to choose. So you can choose the wetting phase. Water looks fine to me, and non-wetting phase, oil. Then when you scroll down, you see the contact angles. So water contact angle is 40, and for oil is 140. But you see different material IDs. You can set up this contact angle for up to 4 different materials. The Idaho grain we're looking at here and using as an example is a pretty simple system, and it's got only quartz in it mostly. You might have a mixture of different types of rocks. Sometimes you might even have clay that might have its own permeability and the different contact angles. And those different materials and the different contact angles in this particular simulation, you can set them up separately. So it doesn't need to be one type of solid. You can have a multiple solid materials in the system. Okay. And another parameter I want to mention is this fluid interface step size. The default setting is 32. You can make this smaller to do more precise calculation, but that makes your calculation take longer too. And another thing is when you're looking at all those parameters and you wonder, what is this parameter? What difference does it make? You can put your mouse cursor to this, for example, then you see the explanation of each parameter. So you can get an idea what it is. And I should also mention that they have a very good manual, so you can always refer to the manual to understand more details. Okay, so once you set those parameters, you click run. This one takes hours, so I'm not going to run right now and save the results. So this one is going to be here. Let me open this one. Okay, so once you run this inhibition process simulation, you will know what, this is one of the parameters we mentioned multiple times today. You will know what the irreducible water saturation is. And more importantly, you will know what the residual oil saturation is. This is the oil that gets left behind. And we have those numbers because we did a full simulation of the capillary pressure curve. The red line is the primary drainage. Then you start your first inhibition process. First, it happens spontaneously all the way here. Then you force the rest of the process and you get to this point. So you can kind of see that there is about a 15% of oil left. This line never gets to 100 or 1. And that's the residual oil amount you can calculate without running a whole lot of experiments. Okay, so I hope this gives you an idea on how you can run those simulations and then maybe replace a lot of expensive and time-consuming experiments by simulation to gain the insight you need. Okay, now let me switch back to the PowerPoint. Let's see. And let's wrap this up. Okay. So you just learned how to calculate the capillary pressure and how to get relative permeabilities, then how to simulate drainage and inhibition processes. I think we have, more than a few minutes. Take more questions.
We do. So thank you, Angela, Aya, and Arn. We do have time for a short Q&A. We've got 3 questions. They're all sort of related. So I'm gonna start off with the first one is, where do you find the contact angle data for different materials? So Arn, do you have a database within Geodict for all these different materials?
So we are having a database, but at the moment not for the contact angles. So normally we have a contact angle range. So for oil, that's normally between 138 and 142 or so. And so you just take the value right in between with the 140. We left it open to be manually adjusted by the user. So of course, if you have a measurement for some kind of material, you can then insert your own parameters here. You have a accurate simulation then.
Okay, perfect. The next question is also comes down to oops, more questions coming in. Okay, are there limitations on the fluid pairs that you can use in Geodict? So for example, somebody wants to look at nitrogen brine as the wetting fluid versus oil. Perhaps.
So very good question as well. So of course you can insert different materials inside of Geodict. The only thing you have to know for that kind of simulation is the interfacial tension between the fluids and the contact angle of each of the fluids then. Yeah, but of course you can enter every possible combination of 2-phase flow pairs here.
Okay. All right. Now this is my question from something that you had mentioned earlier related to contact angles and that's segue. So you mentioned, it sounded like, did you say that the contact angle can change? So say if with water, that contact angle changed if the water was on an oily surface. So are you accounting for those changes during your simulations, or did I misunderstand?
No, yeah, right. We are accounting for these changes. And there was also a checkbox in the forced capillary pressure command I just showed. And if you check that box, it accounts for these oil-wet contact angles.
Oh, excellent. Okay.
But you can also run the simulation completely without these adjusted contact angles as well. And then you do some kind of a sensitivity study. How big is the effect of my changing contact angles for each simulation then?
Okay. All right. And then this is the final question that has come in is they're questioning, is the resolution of the CT or the resolution of the CT data could be actually the limiting parameter in your simulations, particularly for systems with narrow pore throats. How do you manage that with your simulations? Is kind of, I think that's what they're trying to ask here.
Yeah, also a very good question. Of course, the data which comes in is always limiting us because with the CT data, you're only getting a kind of small field of view. And then your resolution might not be good enough to resolve all the details within your pore throats. Of course, if you have a very complex structure like an unconventional carbonate, you might have microporosity as well. And for these kind of rocks, it's very difficult to determine across the scales how big my residual oil phase would be, because you cannot resolve in the CT scan these very tiny pores inside of your carbonate here. So yeah, we're still working on an approach across the scale. And for the single phase flow, we already have that approach, as Aya showed in the last webinar. But for 2-phase flow, it's much more complicated.
Okay. Well, thank you.
So for the measurement parts, and I just want to add one thing. When CT resolution is not good enough, I believe it's more common to use scanning electron microscopy instead to achieve a higher resolution. Your field of view gets a lot smaller, but you can achieve a higher resolution. And when you think about rocks like shale, CT really doesn't have a chance to do good pore analysis. If you go to synchrotron beamline, maybe, but it's more common to use SEM.
Okay. All right. So that is actually, that's all the time we have for questions. We did actually get through all of our questions.
Okay.
If you have any additional questions, again, please don't hesitate to reach out. Oh, wait, we might have had one more question come in. Let me get to that real quick. Can you merge the data from the SEM and CT? So could you actually use both data sets in Geodict?
So at the moment, and a feature which is already implemented in Geodict is that you can define porous voxels. These are voxels that bear the information of the scale below. So for example, you have shale rock, and then you're having PIP SEM data of that rock, where you have determined your permeability on, and then you have a micro CT scan, which does not resolve all the features of that structure. And then you can determine the region in which you have not enough resolution to resolve the features in a micro CT scan. And then for these voxels, you can determine a different permeability. But at the moment, that works only for the single phase flow approach, not for the two-phase flow approach.
Okay. Okay. All right. So now that is all the time we have for questions.
Okay.
So as I said earlier, a recording of the workshop will be available tomorrow, and an email will go out to everyone who registered with instructions on how to view the recording. Links to the resources mentioned today will also be shared on that landing page. So be sure to come back next month when we'll be hosting the first session of our next deep dive series into filtration analysis on October the 12th at 2 p.m. Eastern, 11 a.m. Pacific. Look forward to seeing you then. Thank you for joining us, and we'll see you again in October. Bye now.
Thank
See you.
you.
Bye.